Unlocking the universe. Why understanding complexity isn't just smart, it's essential. Introduction. Complexity is a dance that plays out across our universe, from the intricate designs on a seashell to the bustling dynamics of a city. Governed by simple rules, these systems create harmonious masterpieces across fields like biology, physics, economics, and even art. But don't be fooled, this isn't just academic whimsy. Understanding complexity is vital for shaping our world, from the way we build technology to how we interact socially. This phenomenon weaves its way through a myriad of disciplines, whether it's individual cells culminating in the tapestry of life, basic buying and selling decisions leading to global economic trends, or simple algorithms resulting in complex data structures. Simplicity gives birth to complexity. These fields may seem unrelated, yet they're bound by a common thread: the emergence of intricate systems from basic principles. As we venture deeper, you'll find that complexity isn't a chaos to be tamed, but a wellspring of insights. It equips us with the ability to make more nuanced decisions. Instead of resorting to blunt force, we can make subtle adjustments, nudging systems towards desired outcomes, or knowing when such orchestration is futile. This isn't just intellectual fodder, it's a toolkit for navigating a world teeming with both predictability and unpredictability. Join us on this captivating journey, not just to scratch an intellectual itch, but as a meaningful blueprint for action. Understanding complexity isn't about mere curiosity. It's about equipping ourselves to interact wisely with a world full of both order and chaos. Simplicity breeds complexity. Self-organization. Self-organization is an entrancing principle where simple entities interact locally, without central coordination, giving rise to more elaborate global patterns or structures. It's as if each individual is following its own mini rulebook. Yet the collective result is a phenomenon far beyond the capabilities of any single unit. Take, for instance, the mesmerizing ballet of a flock of birds. Each bird adheres to a few basic rules. Maintain a specific distance from your neighbors, align yourself with the birds close to you, and avoid collisions. While each rule is straightforward, the end result is a spectacle of coordinated movement that can make it appear as if the flock is a single organism. In the underwater world, schools of fish demonstrate a similar phenomenon. Each fish keeps a watchful eye on its immediate neighbors, adjusting its speed and direction to maintain cohesion. There's no master fish dictating the movement, it's every fish for itself. Yet together they form a unified school that can change shape and direction like a well-oiled machine. In both examples, the rules are so simple they can almost be called intuitive. Yet they lead to behavior that is stunningly complex and adaptive, providing survival advantages like predator evasion and efficient foraging. This idea of self-organization stemming from minimal rules isn't just poetic, it's practical and often essential for the very existence of these groups. Case example: Conway's Game of Life. In computer science, Conway's Game of Life stands as a compelling testament to the potential complexity that can arise from deceptively simple rules. Created by British mathematician John Conway, this cellular automaton consists of a grid where each cell can be either alive or dead. The game proceeds in steps or generations, with each cell's fate determined by its 8 neighbors according to straightforward rules. 1. A live cell with fewer than 2 live neighbors dies, underpopulation. 2. A live cell with 2 or 3 live neighbors stays alive, stability. 3. A live cell with more than 3 live neighbors dies, overpopulation. 4. A dead cell with exactly 3 live neighbors comes to life, reproduction. At first glance, these rules might seem too simple to produce anything beyond basic patterns. Yet, the emergent behavior can be startlingly complex. Structures known as gliders, spaceships, and oscillators can form, morph, and even vanish, only to reappear in different configurations. Some of these patterns have been shown to be Turing complete, implying they can simulate any computation under the right conditions. The spontaneous dynamism of Conway's Game of Life isn't directed by any central authority or underlying plan. It's pure self-organization at work. This quality makes the game a powerful, multidisciplinary tool, extending its relevance far beyond the realm of computer science or mathematics. Researchers and thinkers have adopted its principles to probe complex phenomena in multiple fields. For instance, in biology, Conway's game serves as an illustrative model for cellular automata, shedding light on processes like cellular development and the patterns observed in biological systems. The absence of a master planner in the game resonates with the tenets of evolutionary biology, where simple mechanisms like natural selection can lead to the complexity of life as we know it. In the sphere of philosophy, the game poses intriguing questions about determinism and free will. If a system as uncomplicated as Conway's can produce unpredictability and complexity, what does this imply for our understanding of human behavior and decision making? Could our actions and choices be the result of simple rules interacting in complex ways without the need for some overarching, deterministic plan? Thus, Conway's game of life becomes more than just a captivating pastime. It's a versatile metaphorical framework that offers valuable perspectives across various domains, from understanding the intricacies of life to grappling with existential questions. In essence, Conway's game shows that complexity doesn't always require complicated laws. Sometimes the richest complexity emerges from the most basic soil, simple rules that interact in unpredictable ways, birthing a world of endless possibilities. Emergence. Simple interactions, unexpected patterns. Often, the allure of complexity lies in its unpredictability, the sheer defiance of straightforward calculation or even human intuition. When individual components of a system interact according to basic rules, the system's global behavior can manifest in ways that are startlingly complex, showcasing what is known as emergent behavior. Take the simple act of dropping grains of sand onto a table, one at a time. Each grain adheres to the law of gravity, accumulating until the mound reaches a specific slope. When this happens, avalanches occur, redistributing the grains. Despite each grain following a straightforward rule, pile up until the slope becomes unstable, the ensuing pattern of avalanches is intricately complex and even chaotic. Similarly, let's dive into the stock market. Each trader is guided by a set of personal rules or instincts, shaped by their unique experiences, emotions, and interpretations of market trends. When these individual choices aggregate, the market exhibits wildly fluctuating conditions, from soaring bull markets to jarring crashes. What makes it even more elusive is the feedback loop. Charts and market indicators influence traders' decisions, while those very decisions in turn shape the next set of charts. This recursive relationship adds another layer of unpredictability. Even sophisticated algorithms and financial models, crafted to foresee market behavior, often fall short in their predictions. They struggle to account for the human variables and feedback loops, underlining the elusive and complex nature of market dynamics. The key takeaway here is that in complex systems, the whole behaves in ways that are not merely the sum of its parts. The interactions between individual components give rise to new, unpredictable properties, qualities that couldn't have been foreseen by examining each element in isolation. This phenomenon, known as emergence, serves as a cornerstone for understanding how simple rules can give birth to unexpected and often stunning patterns. Case example: the ingenious ant colonies. If you've ever marveled at the industriousness of an ant colony, you've witnessed a stunning display of self-organization and emergent complexity. Each ant seems to operate on a set of straightforward rules: search for food, follow pheromone trails, carry food back to the nest, and so on. Individually, an ant might appear to be carrying out a simplistic task, yet collectively, these tasks add up to something much more grandiose. For example, consider how ants construct their nests. There's no architect ant handing out blueprints or delegating tasks. Instead, each ant picks up a grain of dirt or a leaf and deposits it based on environmental cues and pheromone signals from its peers. This isn't just random activity, it's akin to a bottom-up design strategy. Over time, as thousands or even millions of ants engage in this behavior, intricate networks of tunnels and chambers emerge. These are optimized for ventilation, food storage, and defense, adapting as conditions change, like new threats or food sources. Moreover, the collective foraging behavior of ants resembles techniques found in advanced computer algorithms designed to solve optimization problems. When an ant finds food, it lays down a pheromone trail. Other ants then vote with their feet by choosing to follow stronger pheromone trails, thus reinforcing the most efficient pathways. This decentralized decision-making process leads to highly effective problem-solving without a leader or central plan, showcasing a form of swarm intelligence that transcends individual capabilities. What's truly captivating is how these basic behaviors manifest into complex colony structures and adaptive strategies without any centralized planning. Each ant acts like a cog in a machine, but it's a machine that adapts, evolves, and thrives based on the collective interactions of its individual rule-following components. The dance of order and chaos, feedback loops. In the quest to understand the intricate dance of complexity, one cannot overlook the role of feedback loops. These loops can be broadly categorized into two types: positive feedback and negative feedback. Each plays a distinct yet crucial role in the overall behavior of complex systems, influencing either their stability or propensity for change. Positive feedback, the amplifier. Positive feedback is essentially a self-reinforcing mechanism. It amplifies initial conditions or changes within a system, often leading to exponential growth or rapid shifts. Think of it like a snowball rolling down a hill. As it gains momentum, it picks up more snow, growing larger and faster with each revolution. In social contexts, this could be likened to viral trends, where an initial burst of popularity spirals into widespread cultural phenomena. Negative feedback, the stabilizer. In contrast, negative feedback aims to bring a system back to a state of equilibrium whenever it deviates from a set point. It's like a thermostat that adjusts the heating or cooling to maintain a desired room temperature. In ecological systems, predator-prey relationships often serve as a classic example of negative feedback. When the population of prey increases, predators find more food, their numbers increase, and subsequently, the prey population is reduced, stabilizing the system. Both positive and negative feedback loops are essential in shaping the dynamics of complex systems, whether it's in the stock market, climate systems, or human behavior. What's especially fascinating is how these loops often interact. In many instances, negative feedback loops act as a regulating mechanism, preventing positive feedback loops from spiraling a system into chaos. This interaction becomes a crucial factor in the stability and adaptability of complex systems. While positive feedback loops drive change and innovation, they can lead to instability and collapse if left unchecked. Conversely, negative feedback loops contribute to resilience and homeostasis, but can sometimes stifle adaptation and growth. The interplay between these two types of feedback is often what keeps complex systems in a state of dynamic equilibrium. Case example: the intricacies of climate systems. When discussing the complexity of interconnected systems, Earth's climate presents a compelling case that is worth examining regardless of one's views on the topic. This intricate system is guided by a range of feedback mechanisms, both reinforcing and counteracting, that contribute to its behavior over time. Ice albedo feedback, a chain of events. Consider the phenomenon known as the ice albedo effect, which is a straightforward sequence of cause and effect. Ice and snow reflect sunlight, keeping temperatures moderated. When some of that ice melts, darker ocean surfaces are exposed, which absorb more heat. This natural cycle demonstrates how an initial change can lead to further changes, a self-reinforcing mechanism that has been observed across various systems. Carbon capture, Earth's balancing act. On the other end of the spectrum, we find balancing mechanisms like carbon capture by forests, soil, and oceans. This process serves to regulate the amount of carbon dioxide in the atmosphere, offsetting some of the effects of other variables. Whether you attribute current climate trends to human activity, natural cycles, or a mixture of both, understanding these balancing processes is essential for a full picture of climate dynamics. The synergy of systems. What makes climate so fascinating is the interplay between these feedback loops. Remove or alter one, and the system doesn't merely revert to a prior state, but finds a new equilibrium that might be less intuitive to predict. For instance, if ice melts and exposes soil that releases methane, we see another layer of complexity emerge. Human choices, the X factor. In any discussion about climate complexity, the role of human choices cannot be overlooked. Whether it's policy decisions on carbon emissions or individual habits like consumption, these choices add another layer of complexity to an already intricate system. What's particularly challenging is that these human-induced variables often produce outcomes counter to their original intent due to the system's inherent complexity. For example, well-intentioned policies to reduce carbon emissions in one sector might inadvertently lead to increased emissions in another, or conservation efforts in one area may shift exploitation to a different, less regulated ecosystem. The key takeaway is that the human element introduces both potential solutions and complications, making predictive modeling even more challenging. Thus, an understanding of the complex interactions and feedback loops at play is essential for making more informed, effective decisions, and to be more humble about our certainty. The aim here is not to alarm, but to enlighten. Understanding the complexity of climate systems can inform discussions and decisions around environmental stewardship, which is a shared concern for all who inhabit this planet. Grasping these feedback mechanisms can help us maintain humility while we attempt to anticipate consequences, both intended and unintended, of changes to this intricate system. Unintended consequences, navigating the complexities of order and chaos. Building on our exploration of the delicate interplay between order and chaos, we delve further into real-world scenarios that vividly illustrate this dynamic. The following case studies serve as additional examples, showcasing a common principle: the law of unintended consequences. This principle suggests that actions in complex systems often produce unexpected and counterproductive outcomes. Each case sheds light on how well-intentioned policies and solutions can inadvertently lead to more complex, sometimes chaotic situations, underscoring the need for careful consideration and holistic understanding in decision-making processes. The Cobra Effect: misguided incentives and unintended consequences. During British colonial rule in India, an initiative to control the venomous cobra population in Delhi led to an ironic twist. The British government offered a bounty for every dead cobra, intending to reduce their numbers. This policy initially saw success, with many cobras being killed. However, it soon backfired spectacularly. Realizing the monetary benefit, people began breeding cobras to earn the bounty. When the government ceased the program upon learning this, breeders released the now worthless cobras, resulting in an even larger cobra population than before. This example underscores the unintended consequences of poorly thought-out incentives in complex systems. Biofuels: environmental solutions leading to ecological problems. In a global effort to reduce dependence on fossil fuels and mitigate carbon emissions, many nations turned to biofuels. This switch, while environmentally motivated, led to an unexpected ecological crisis. Large swathes of forests were cleared to cultivate crops for biofuels, resulting in significant carbon dioxide emissions and disruption of ecosystems. The deforestation associated with biofuel production negated many of the anticipated environmental benefits, illustrating the delicate balance between alternative energy solutions and ecosystem preservation. The diesel dilemma: environmental policies and public health. European policies once favored diesel cars as a greener alternative to gasoline vehicles, aiming to reduce CO2 emissions. However, this policy had unforeseen repercussions. Diesel engines, while emitting less CO2, released high levels of nitrogen oxides, contributing to air pollution and public health concerns. Many European cities faced increased air quality issues, highlighting the complexity of environmental policymaking and the challenge of predicting long-term impacts of seemingly beneficial technologies. Nonlinearity and stochasticism: the wildcards of complexity. If complexity teaches us one thing, it's that not all inputs produce proportional outputs, and not all outcomes can be precisely predicted. This is where the concepts of nonlinearity and stochasticism come into play, serving as wildcards in the intricate game of complexity. Nonlinearity: the curveball. Nonlinear systems defy our intuitive expectations by delivering outputs that are not directly proportional to inputs. Imagine pushing a snowball down a hill. Initially, a small push yields a slow roll, but as the snowball grows, that same small push triggers an avalanche of activity. In financial markets, this could manifest as sudden surges or drops that seem out of sync with underlying economic indicators. Stochasticism: the roll of the dice. Stochasticism, or randomness, introduces another level of complexity. Even with a perfect understanding of all the rules and variables, predicting an exact outcome becomes virtually impossible due to random factors. For example, in evolutionary biology, random mutations can drastically alter the course of an entire species. Or in weather systems, minor fluctuations in atmospheric conditions can lead to vastly different weather outcomes. Most of this randomness itself often is merely a complexity, as of yet, beyond our ability to measure and predict. The dance of nonlinearity and stochasticism. These two concepts often interact in fascinating ways. Nonlinearity might amplify the effects of a random event, creating a disproportionately large impact. Conversely, stochastic events can introduce enough randomness to disrupt a potentially stable, nonlinear system. The study of nonlinearity and stochasticism isn't just academic, it's deeply practical. Understanding these principles can guide our actions and decisions in navigating complex systems, whether they're social networks, financial markets, or natural ecosystems. Case example, from Wall Street to weather forecasts. Two realms where nonlinearity and stochasticism come into vivid play are stock markets and weather patterns. While vastly different in nature, they share the complexity and unpredictability that make them both fascinating and challenging to understand. Stock markets, betting on uncertainty. At first glance, one might assume that stock prices should directly correlate with a company's performance or broader economic indicators. However, anyone who's watched Wall Street knows that's seldom the case. Market psychology, geopolitical events, and even rumors can send stocks soaring or plummeting in nonlinear ways. On top of that, the inherent randomness, like unexpected corporate announcements or global events, adds a layer of stochasticism that makes precise prediction a Sisyphean task. Weather patterns, the butterfly effect. In meteorology, the butterfly effect encapsulates the idea that small changes in initial conditions can lead to dramatically different outcomes, a classic case of nonlinearity. Accurate weather forecasting is further complicated by stochastic factors like sudden temperature fluctuations or wind pattern shifts, which can alter weather courses in unpredictable ways. The common thread. What binds these examples together is the principle that understanding the underlying mechanisms can guide our expectations, if not our predictions. In stock markets, hedging strategies and diversification aim to mitigate the effects of unpredictability. In weather patterns, improved data and modeling offer better, though still not perfect, forecasts. Studying these examples gives us insight into how nonlinearity and stochasticism function in real-world scenarios, highlighting the importance of understanding these principles when dealing with complex systems. While it's true that nonlinearity and stochasticism make exact predictions challenging, they don't render systems entirely unpredictable. Quite the opposite. By employing statistical methods and probability models, we can often predict the range within which a system's behavior is likely to fall. For example, weather forecasts might not pinpoint the exact temperature, but they can offer a likely range based on historical data and current conditions. In financial markets, risk assessments can provide an idea of potential gains and losses within a certain confidence interval. This is not fortune-telling, but a sophisticated use of data and modeling to navigate the seas of complexity. Although the waters are never entirely still, understanding their general patterns can help us steer more skillfully. The unpredictable beauty of complexity, computational irreducibility, the end of shortcuts. In a world obsessed with efficiency and quick results, the concept of computational irreducibility serves as a humbling reminder that not everything can be simplified or shortcut. Some systems demand to unfold in their own time and way, resisting any attempts to predict their outcomes through computational shortcuts. No crystal ball take, for instance, cellular automata like Conway's Game of Life. Even though the rules are dead simple, the patterns they create are so complex that there's no way to leap directly to an end state without actually running through each step of the algorithm. You can't just plug variables into a formula to know how a configuration will look after, say, 100 iterations. You have to let it play out. The weather forecast revisited. Even with the most advanced supercomputers, meteorologists can't precisely forecast weather conditions months in advance. Each passing moment introduces a new layer of complexity that necessitates recalibration, making it computationally irreducible in a practical sense. In a very real way, the universe is its own computer, running its own calculations on what the next state of the universe will be. To perfectly predict its outcomes would take a computer larger than the universe to complete the calculations faster. Otherwise, you could just wait and see what the universe's results are. Maybe the answer is 42. The futility of shortcuts. The essence of computational irreducibility lies in the understanding that some processes have to be experienced in real time, each step informing the next. In a world where we often want to skip to the end, this can be both frustrating and enlightening. The futility of shortcuts in these instances teaches us patience and offers a more nuanced understanding of the systems at play. By acknowledging the limits of our predictive powers and the intrinsic complexity of certain systems, we come to appreciate the unpredictable beauty that complexity offers. This forced patience can sometimes lead to serendipitous discoveries or insights, as allowing things to unfold naturally can reveal patterns or connections we wouldn't have otherwise noticed. It's a lesson in humility, reminding us that not everything bends to the will of our calculations and expectations. Case example: cellular automata and the enigma of mathematical systems. While the concept of computational irreducibility can often feel abstract, it's dramatically brought to life when examining cellular automata and certain mathematical systems. These enigmatic constructs challenge our intuitive understanding of predictability, making them perfect subjects to delve into for a deeper understanding of complexity. Cellular automata, the simple yet unpredictable. In cellular automata like Conway's Game of Life, a grid of cells evolves over discrete time steps according to a set of simple rules. Yet, despite the simplicity, predicting the end state without actually running the algorithm proves impossible. Sure, you can analyze it for general behavior or look for repeating patterns, but there's no computational shortcut to know exactly what configuration will appear after a given number of steps. Mathematical systems, the rabbit hole of unpredictability, fractals like the Mandelbrot set, are generated by iterating a simple equation over and over. Despite the equation's simplicity, the resulting pattern is infinitely complex, displaying self-similar structures at any level of magnification. No shortcut exists for determining the intricate detail found at any arbitrary point in the pattern without going through the iterative process. Nonlinear equations, such as those encountered in chaos theory, add another layer of computational depth. Even a slight variation in the initial conditions can lead to dramatically different outcomes, known as sensitive dependence on initial conditions, or the butterfly effect. Solving these equations isn't just a matter of plugging in numbers. Each step in the solution could influence the next, making them intrinsically computationally irreducible. In both instances, the systems demand that you engage with them step by step to unveil their complexities, defying attempts to foresee their behavior through any computational shortcuts. Learning to embrace uncertainty. The key takeaway from these examples is that computational irreducibility is not just a theoretical concept. It's an aspect of the world around us that impacts how we approach problem solving and prediction. Recognizing that some systems resist shortcuts is a form of intellectual honesty, and it opens the door to a deeper understanding and appreciation of the inherent complexity of our universe. These cases serve as a stark reminder that the journey through complexity often requires patience and a willingness to engage with systems on their own terms, rather than seeking quick and reductive solutions. Entropy. Entropy, the cosmic accountant of disorder and uncertainty. When discussing complexity, the concept of entropy invariably takes center stage. This ubiquitous principle permeates various fields, from thermodynamics to information theory, acting as a universal measure of disorder and uncertainty. In essence, entropy sets the rules for how systems evolve over time, governing everything from cooling coffee to data encryption. At its core, entropy quantifies disorder and informational gaps in systems. Understanding entropy isn't just an intellectual exercise, it's a tool that unlocks insights into the operational fabric of various systems, guiding the limitations and possibilities across biological, physical, economic, and digital landscapes. Understanding entropy is like holding a key to decode the innate complexity of systems around us. The thermodynamic perspective. In thermodynamics, entropy is often described as a measure of disorder within a closed system. As these systems naturally evolve, They tend to gravitate toward a state of maximum entropy, commonly known as thermal equilibrium. Here, energy disperses as randomly as possible, which usually results in an even distribution. This principle underlies natural phenomena like ice melting or the diffusion of perfume in a room. While these processes generally follow predictable paths, there's an astronomically small but non zero chance that events could unfold differently. Your coffee could freeze in its cup, or all the air in a room could accumulate in one corner, leaving you gasping for breath until it redistributes. Information theory, the uncertainty principle. In information theory, entropy serves as a gauge for the unpredictability of a set of possible outcomes. For example, the entropy of a coin toss is lower than that of rolling a die because the coin has fewer potential outcomes, making it inherently less uncertain. Consider the atoms in your cup of coffee. The chance that they spontaneously rearrange themselves into a freezing configuration is exceedingly slim. The vast number of possible atomic arrangements overwhelmingly favor a state of random, uniform motion. Similarly, the likelihood that all rooms' atoms would find their way into one corner, depriving you of breathable air, is infinitesimal. When you chart out all conceivable atomic positions, the overwhelming majority will show a fairly even and random distribution. This occurs not due to any guiding force, but because there are simply more ways for things to be disorderly than orderly. Markets, ecosystems, and beyond. Entropy as a universal constant. Entropy doesn't just limit itself to the realms of physics and information theory. It's a ubiquitous force that manifests in economic and ecological systems as well. In markets, forces naturally gravitate toward a state of equilibrium, akin to thermal equilibrium in physics. This is why stock prices fluctuate around a mean value over time, as buyers and sellers push and pull in a sort of financial entropy. Similarly, in ecological systems, the distribution of species often mimics a form of biological entropy. Predators and prey, plants and pollinators, all strive towards a balanced coexistence, a dynamic equilibrium that reflects the many possible states the system can inhabit. The concept even bleeds into the fabric of our everyday experiences, governing the randomness in everything from the ebb and flow of traffic to the viral spread of rumors on social media. In each case, entropy serves as a measure of uncertainty and complexity, influencing systems large and small, from the cosmic to the quotidian. A guiding force, entropy helps us understand both the constraints and potentials inherent in diverse systems. Whether examining melting ice or volatile stock markets, entropy acts as a cosmic accountant, tabulating disorder and nudging systems toward equilibrium. Acknowledging entropy's universal role deepens our insights into complex systems and enriches our understanding of a universe that thrives on unpredictability and chaos. Case example: thermodynamics and information theory. Entropy in action. Thermodynamics, the entropy of everyday life. Consider a cup of hot coffee left on your table. Over time, it cools to match the room temperature. This change is a classic case of thermodynamic principles at work, as entropy nudges the system, comprising both the coffee and the surrounding air, toward thermal equilibrium. Molecules in the hot coffee transfer their energy to the cooler air through atomic interactions, gradually evening things out. It's akin to dropping marbles into a bathtub. They roll and bounce off each other until settling into a resting state. In this scenario, entropy takes center stage, steering the system toward a more disordered or equilibrium state. Information theory, entropy in communication. In the realm of digital communication and cryptography, entropy is a critical measure of unpredictability. When you send a secure message, higher entropy ensures that the message is more resistant to decoding attempts. This principle is much like a combination lock. A simple lock with one dial and a few numbers has low entropy and is easy to crack. In contrast, a complex lock with multiple dials and many numbers offers higher entropy, making it far harder to decode by brute force. This example illustrates how entropy is a pivotal concept not just in physics but also in our modern world, digital or otherwise. The common thread, what unites these disparate examples, is the omnipresent role of entropy in determining the direction of processes. Whether it's a physical change like the cooling of coffee or a computational task like secure communication, both systems are governed by the universal principle that systems naturally tend toward higher entropy, whether it's the spreading out of thermal energy or the scattering of digital bits in a cryptographically secure way. The robust and adaptive nature of complexity, adaptation, and redundancy, how systems change and stabilize over time. Understanding adaptation and stability in dynamic systems. One fascinating trait of complex systems is their dynamic, adaptive nature. Far from being static, these systems are living, changing entities that react to both external forces and internal shifts. Over time, they self-adjust, grow, and frequently toughen up in the process. Consider an ecosystem disrupted by a new predator. At first, this throws the system into disarray. But with time, adaptive mechanisms emerge. Prey may evolve new defensive tactics, and the predator could face its own set of challenges, ultimately bringing the system back into balance. In tech networks, redundancy and error correction algorithms function as safeguards, contributing to a system's resilience. The secret sauce here is redundancy and diversity built into the system's architecture. Multiple routes or tactics often exist to reach the same goal, enabling the system to adapt to various disruptions. What may look like over-engineering is actually a survival strategy, designed either by people or the natural selection of nature to help the system navigate a diverse array of challenges and emerge even stronger. By grasping the inherently adaptive features of complex systems, we see that change and stability aren't opposites. They're two sides of the same coin, essential for the system's long-term viability. Case example: evolution and city planning. Evolution, the mechanism of natural selection in biological evolution, offers a compelling example of adaptation and redundancy. Gene variations ensure that populations have a rich set of strategies for survival. When environmental conditions change, some traits that were previously irrelevant may become vital, helping the species to adapt and continue thriving. City planning. On a more anthropocentric note, city planning demonstrates how human-made systems also rely on adaptive and redundant structures. Cities often have multiple routes to the same destination to accommodate for road closures or traffic. Infrastructure like power grids and water supplies are built with backup systems to ensure continued functionality during unexpected events. Both evolution and city planning showcase how complex systems are designed, either by natural processes or human ingenuity, to adapt, endure, and stabilize over time. The principle here is clear. Diversity and redundancy aren't inefficiencies, but essential features that make systems robust and adaptable. Markets. In any given marketplace, there might be dozens, hundreds, or even thousands of competing products, each varying in quality, kind, and price. You might ask, why do we need 20 different types of peanut butter? The answer is twofold. Not only does a diverse selection cater to individual preferences, but it also serves as a form of system resilience. A multitude of supply chains, organizational styles, and production processes create a buffer against disasters. There's no single point of vulnerability, and the market continuously adapts to shifts in supply and demand, directing resources where they're most needed. While both natural and human-designed systems embody principles of adaptation and redundancy, there's a key difference: the time scale of their evolution. Natural systems have had eons to fine-tune their complexities through a process of trial and error, leading to a level of resilience and adaptability that's hard to match. In contrast, human design systems are constrained by the limits of our understanding and the time we have to implement solutions. Often, we try to expedite processes, inadvertently overlooking the intricate interdependencies that make a system robust. This leads to vulnerabilities that nature, in its slow march of evolution, has largely managed to weed out. Recognizing this gap can inspire a more nuanced approach to designing systems, one that respects the wisdom embedded in natural complexities. Edge of chaos and attractors, balance between stability and creativity. In complex systems, there exists a harmonious zone often dubbed the edge of chaos. It's a space where the system is neither overly structured nor excessively chaotic, enabling a blend of stability and adaptability. In this unique equilibrium, a system is its most inventive, churning out new patterns and solutions while maintaining its essential functions. Consider an improvising jazz band. While each musician understands the foundational rules, there's room for creative liberty. This dynamic interplay between structure and freedom yields an intricate, yet cohesive, performance. An overly structured approach results in dull repetition, while unbridled chaos descends into cacophony. In the biological realm, this edge of chaos is often where evolution is most effective. There's sufficient genetic stability for survival, but also enough mutability for adaptation. Natural selection acts as the discerning gardener, pruning away the unfit. This delicate balance is not just intriguing, but also instructive for tackling complex problems, whether in engineering, economics, or societal systems. This equilibrium also underscores the significance of attractors, stable states that a system naturally gravitates toward. Grasping these attractors can provide insights into steering a system towards a specific outcome or predicting its natural course. Case example: neural networks and psychological behavior. Neural networks. In machine learning, neural networks typically thrive at this fabled edge of chaos. A too-structured network may fail to generalize its learning, effectively becoming a parrot that only repeats what it has been taught. Conversely, an overly adaptive network risks becoming a jack of all trades but master of none, performing well on known data but stumbling on anything new. It's like a trapeze artist. The goal is to find the perfect swing, neither too loose nor too tight, that maximizes learning. Psychological behavior. The concept remarkably mirrors our psychological lives. Most individuals tap into their highest levels of creativity and productivity when balancing between the orderly and the chaotic. Imagine a scientist in a lab or an artist in a studio. Excess structure could stifle creativity, but a complete lack of discipline could lead to aimlessness. It's akin to finding your personal flow, where the level of challenge is in harmony with your skill set, setting the stage for both innovation and achievement. In both realms, artificial intelligence and human psychology, the ultimate goal converges to strike a dynamic yet stable balance that maximizes both efficiency and creativity. This makes the edge of chaos not just a captivating academic concept, but also a practical navigational tool for optimizing systems. Conclusion. Navigating the labyrinth of complexity, we've unearthed how startlingly straightforward rules can birth elaborate, unpredictable systems. Whether it's the algorithmic elegance of Conway's Game of Life, the resilience of Mother Nature's ecosystems, or the ceaseless ebb and flow of markets, complexity serves as our Rosetta Stone for deciphering the world. From flocking avians to Wall Street's whims, these systems abide by fundamental principles that escalate into an entangled mesh of interconnected components, often proving computationally irreducible in their complexity. The allure of complexity is twofold. It's both omnipresent and interdisciplinary. Whether you're a physicist wrestling with subatomic particles, an ecologist mapping intricate ecosystems, or an economist navigating fiscal waters, the lexicon of complexity offers a shared scaffold for understanding. It's an intellectual melting pot that dissolves academic barriers to expose the universal fibers linking disparate fields. In our quest to fathom the complex systems enveloping us, one epiphany emerges. Mastery over complexity isn't the endgame. It's about learning the ropes for effective navigation. Overconfidence in our ability to control or predict these capricious systems can spiral into unintended, sometimes disastrous, outcomes. While our instincts may prompt us to muscle our way into shaping results, the true art lies in nudging, gentle foundational tweaks that send ripples of resilience and equilibrium throughout the system. But let's not forget our place in the grand scheme of things. Complexity's unpredictable, computationally irreducible essence ought to keep us grounded. We're not lords of this domain, but humble explorers, ever cognizant of our own bounds. In this realm, the dictums of physics and math reign supreme. They are the unyielding and utterly rational monarchs. When our best-laid plans falter, that's not a failure on our part, but a feature of complexity itself, embodying our eternal dance with the unknown. With this newfound practical wisdom, we arm ourselves with a toolkit for erecting systems that are not just functional, but thrive in their unpredictable glory. Yet let's remember, the balance is fragile. If the scales tip into chaos, maybe that's our cue to revisit the basics, to veer away from grand designs and lean into simpler, more naturalistic approaches. By folding in principles like entropy and natural selection, we lay the groundwork for systems that flourish in their mesmerizing unpredictability.